Okay, so 4.3 begins by talking about the difference between a linear function and a nonlinear function. So I'll point out the differences for you here in this little example. So linear functions, well, what do their graphs look like? If you had to take a guess, what do the graphs look like? Yeah, they look like lines, exactly, right? They look like lines. It looks somewhat like a line, right? In some way, shape, or form. It has to be non-vertical though. So if it's straight up and down, it doesn't actually count as a linear function. We're going to get more into that later when we talk about why it can't be a vertical. But for right now, we'll just talk about it's a linear function. So some of the pictures that you could have for linear graphs, right? If each of these represent a little small x and y, you could have a graph that just kind of looks like this, right? This is going straight down. That line right there, that pink line, that would represent a linear function. You could also have lines that are not connected, so kind of like this. That would also represent a linear function. Or you could have lines that are going straight across left and right. That would also represent a linear function, just not up and down. We'll get into that later though. Alright, so if that's what linear graphs or linear functions look like, what do nonlinear functions look like? Well, what do you guys think? If you had to take a guess, what do you think the graphs look like? Yeah, okay. The graphs they're just not linear, right? That's all it really means. Because they could take on so many other different shapes. We just say, well, that they're just not linear. They're not lines and they're not part of lines. Let me give you a few quick examples of what nonlinear graphs could look like. If this is an xy coordinate plane, xy coordinate plane, xy coordinate plane, you might have something that looks like this. And I think Jay mentioned a parabola. That's my best drawing of a quick little sketch of a parabola for right now. You might have something that looks like this, right? That's a nonlinear function. Or you might have individual values that look like this, right? They're just not lines or not part of lines. So we have to have a fundamental understanding between linear functions and nonlinear functions. I'm pretty sure most of us can kind of conceptually see what that is. Alright, we're going to compare two different things here. We're going to compare pizza area versus sauce cost. When we're talking about the pizza area, we're going to talk about the radius of the pizza versus the area, okay? So, I'm going to give you some data here. The data I'm going to give you, if you have a 2-inch radius pizza, then the area is 12.57 inches squared. We're talking about inches to inches squared. If we do a 4-inch radius pizza, I don't need to put inches there, then we're going to have a 50.27 inches squared. If I have 6, it's going to be 113.10. If I have 8, it's going to be 201.06. And if I have 10, it's going to be 314.16. And that's all in inches squared. Okay? So that's one set of data on the left. On the right, let's do sauce cost, and we'll do ounces. And again, we'll start with 2 ounces, and it would cost you 80 cents. This is if you're the owner and you're creating this. So if I have 4 ounces, it's going to cost me $1.60. If I have 6 ounces, it's going to cost me $2.40. If I have 8 ounces, it's going to cost me $3.20. And if I have 10 ounces, it's going to cost me $4. Alright, so what can we say about the relationship of the data on the left, pizza area? Would it be linear or non-linear? The one on the left, the pizza area. Linear or non-linear? Okay, do we know what to look for when I ask that question? How do you answer that question? How do you know if it's linear or non-linear? What are you looking for? How much it increases, right? You're looking for that same value increasing or decreasing, okay? So let's look on the left here. All right? I go from 2 to 4. I go from 4 to 6. I go from 6 to 8. I go from 8 to 10. So what am I increasing by? I'm increasing by 2 every single time. By 2 every single time. Okay, that's a good start. Am I increasing by the same amount on this side every single time? No, I am not, right? I am not increasing by the same amount on that time. So this would be nonlinear. This is an example of nonlinear data because I am not increasing by the same amount for the output value. Let's compare that to sauce cost. Well, my inputs value go from 2 to 4 to 4 to 6, from 6 to 8, 8 to 10. That's all plus 2 every single time. And then what's my cost sauce? How much am I increasing every single time? I'm increasing by another 80 cents, another 80 cents, another 80 cents. So, is the one on the right, the sauce cost, would that be linear or nonlinear?
Yeah.
That would be linear. How do we know? There's a constant increase on both sides. That's exactly right. So I'm increasing both on both sides. So if I was to graph both of these, the graph on the left-hand side, I'll do it quickly for you. The graph on the left-hand side would look something more like this. It would rise more as the radius of my pizza increases. Versus the one on the left, you can imagine that it would look like individual discrete little values as we go up, and it would look like a line. So you're going to have to be able to tell the difference between sets of data given linear and nonlinear. And the way that we do it is where we look for equal increments and increasing both on the left and the right of our table. All right, here's an example for you. And the directions are asking us to write a rule. So what they mean by that is they want a generic statement that relates the input value, which is x, to the output value, which is y. All right, so that's what we're trying to do when we're trying to write a rule. Well, first of all, let's see here. Is this a linear or a nonlinear function? What do you think, Alice? Why do you say it's nonlinear?
Because the rule would have an exponent.
You think the rule is going to have an exponent? What's something simpler that we could define or look at right now and say that, well, I definitely know this is not linear. What do you think?
It multiplies by 2.
Each one multiplies by 2? Okay. You're absolutely right. What I'm looking for was that these don't increase by a constant amount. The difference is not the same, right? But there is something else going on, right? Okay, so I'm looking for the rule. So y has to be something x. All right, let's see here. 2, I could rewrite as 2 to the first. You guys agree with that? 4, I could write as 2 squared. 8 can be 2 cubed. Oops, sorry, they're 3 in the wrong spot. How many of you guys see this little rule here? So what would 16 be? To the fourth. What would 32 be? To the fifth. What would, if I go all the way down to x over here, what would I have to do? 2 to the x. So my general rule would be y equals 2 to the x. And this would be a non-linear relationship because that's not increasing by constant amounts, right? Let's do another example. I'll do called part B over here. I'll give you a table. Actually, I'm going to give you a set of points. I'm going to give you 1, 1. I'm going to give you 2, 4. I'm going to give you 3, 9. I'm going to give you 4, 16. And I'm going to give you 5, 25. And I want you to do the exact same thing. But now I've given you points. Does this change anything for us? No, it's the same information, right? It's the same information as if I gave you a table. If I said x versus y, right? I'd have 1, 2, 3, 4, 5. And then all my y values would be 1, 4, 9, 16, and 25, right? Each of these can be represented as an individual point, right? That's a point right there, that's a point right there, that's a point, there's a point, and there's a... Does everyone see where the points come from? Okay, what would be the rule for this one? Y would have to be equal something. Now, is this a linear relationship? No, definitely not. How do we know it's not linear? Well, because there's not a constant increase on both x and y. Okay, so if it's not a constant increase, it's not linear, so we must be doing something else. Anybody see it? Yeah, Daniel, what do you see, buddy?
It's x squared.
It's x squared, right? Every value is the same thing, right? 2 is the same, or 4 is the same thing as 2 squared. 9 is the same thing as 3 squared. 16 is the same thing as 4 squared. 25 is the same thing as 5 squared. So therefore, any x value you give me, I'm just going to do what to it? Square it. So therefore, y is going to be x squared, and that would be that relationship that I have there. So I have 2 examples of non-linear functions that we can write rules for, all right? Okay, the official directions for this one say, what is the graph of the function rule y equals negative 2x plus 1? Okay? And the way that they want you to do it in this particular section is they first want you to start off by making a table. Alright, so if we're going to start off by making a table, we need some input values. Okay? I'm only going to ask you for 4 of them. Okay? So give me some pretty easy input values. What values of x could we use here?
0, 1,
Okay.
1,
Yep. Negative 1, 0, 1, and 2. Just give me 4. I don't need 10. I don't need 5. Just give me 4. All right? Now, we know that every single y is worth negative 2x plus 1. Okay? So when I plug in the y values here, I'll do it in a different color for you. I'm going to get this. I'm going to get y is going to be negative 2. What's the x value that I'm plugging in here? Negative 1. And then I'm going to add 1. So how much is all that worth?
3.
That's worth 3, right? So therefore, now I have a coordinate, an xy coordinate, and that first coordinate is negative 1, comma 3. See how I did that? All right, let's do 0. 0 is really easy, right? So that's going to be negative 2 times a 0 plus 1. How much is that worth? That's worth 1, so I get 0, comma 1. All right, let's do 1. Okay, y is going to be worth negative 2 times 1 plus 1. How much is that worth? That's worth negative 1. So I get 1, comma negative 1. And then it's going to be y is worth 2 times 2, and then we're going to add 1 to that. So what does that give me? Negative 3. So I'm going to get 2, comma negative 3. Once I have at least 4 points, then we can go over and we can easily make the graph. All right? So whenever you're making a graph and you're plotting some points, please use a straight edge so that we can clearly see where the points need to go. All right. Also, it's important that we label our axes so we know which is which. Here's x and here is y. All right. So I have negative 1, comma 3. So negative 1, comma 3 would be this location right here. That's negative 1, comma 3. All right. Where's 0, 1, everybody? At the origin, then up 1 unit. Very good. Okay. And then I have 1, negative 1. So over 1, down 1. Good. And then I have over 2. And then down 3. All right. In this particular case, since I was told that I'm graphing a line right here, this is a linear function, then x can take on any value that it wants, and it does not have to be these individual points. So that being the case, it would make sense for me to then connect all of the lines here. So then I would take this and I would connect all the lines the best that I could. And that's pretty much the best I can do without using a ruler right now. So then I would have my graph y equals negative 2x to represent the function rule. Okay, so when we talk about continuous data versus discrete data, here's what we mean by that, right? Continuous data is an unbroken line. It's a line that can take on any values between of x for x and y. So the one on the left, this would be considered continuous data. This is a continuous line. The one on the right, where I have individual pieces of information, that would be considered discrete. All right. So I'd have individual pieces of data that can be displayed in a graph. That would be discrete data. Continuous data is a sliding scale that can be used. I could take on values of like 3.2, 3.23. I can slide anywhere I want on the x value. So continuous versus discrete comes up a lot in this particular section. All right? Fair enough for continuous discrete? Okay, I've got one more thing to do for you, and it's out of the book. So I'm going to show you a picture out of the book, for instance.